Hey everyone, so this week we are focusing on structural geology, which is actually, I think, a pretty fun topic. And so structural geology is just thinking about how and why rocks get deformed or bent or broken, and how we classify or describe different deformed rocks. So let's talk a bit about this process of rock deformation. So the definition of deformation is just that process by which rocks are either bent or broken when some type of stress is applied, right? So we create rocks through our three rock classification processes, right? We either create an igneous rock, sedimentary rock, or metamorphic rock, right? And then we've created this solid material. And then after that rock has been formed, and as it's hanging out either on the landscape or underground, then it is subjected or can be subjected to some type of stress. And when that stress is applied, that rock can either bend or break as a result of this stress. And so there are three main types of stress. We have compression. Compression is stress moving towards, right? Tension is stress pulling away, and shearing is movement sort of sliding next to each other. And when we apply those three types of stress, the rock is going to respond in a certain way. It will either behave ductily or it will be ductile, which means that it will be sort of deformed, bent, but not broken, or it can respond brittly or act brittle, in which it breaks. So here these pictures are showing, here's an example of ductile deformation. Right, see how that rock's just been and sort of smushed together and gotten wavy, but it's not broken. And then here we can see we have brittle deformation where we have a number of breaks in our rock that we can see by these lines here. You can definitely tell this rock is broken based on this white layer and how it's offset. All right, so when we're thinking about stress, the definition of stress is just any force that's acting to deform rocks. And so if we kind of go back to those words that we were using when we were talking about metamorphic rock formation, stress, think of that as any type of directed pressure. Stress is the result of any pressure exerted in a certain direction. And again, we have those three types of stress. So we have compression, which is the force of pushing objects together. So you can think about compressive forces being associated, right? So far in class, when we talked about plate tectonics, right? One type of compressive stress would be at a convergent boundary where the plates are moving towards each other. Tension or extension forces is the force of pulling objects apart, right? So we have tension forces at our divergent plate boundaries. And then shear is the force of objects sliding past each other. And our shear forces, an example in plate tectonics, of course, would be when we have a transform boundary. So we have three main types of stress: compression, tension, and shear, and those are going to work on solid rocks to deform them in some way. And when we deform those rocks in some way, we refer to that as strain, which is the actual change in shape of the rocks because of that stress. So that's kind of what this diagram is showing over here, where we have the force shown by our arrows, and then you can see the strain on the rocks and how that shape has changed, right? So originally, every single one of these would have been a rectangle, right, with our 3 layers. Looks like almost Neapolitan ice cream or something. Maybe I just need a snack. I don't know. Right, so originally we had a rectangle, and then as our force is acting on that rectangle, you can see how each of those different types of stress are resulting in different strains. All right, so as I mentioned previously, there are 2 types of deformation. The first type of deformation is called ductile deformation. And ductile deformation is when a rock is bent or folded because of that stress being applied. And so here, for example, is a conglomerate. Remember, a conglomerate is a sedimentary rock made up of rounded pebbles. And so originally, these were all round spherical pebbles that were cemented together. And then it has undergone some type of deformation because of some stress, and it behaved ductily or plastically. So when we have ductile deformation, it means that the rock was deformed by bending or folding, and it doesn't break, right? It just kind of gets bent. So one example I always think of is silly putty, right? So think back to when you were a kid and you had silly putty, or really also like non-Newtonian fluids, like if you ever played with cornstarch and water or oobleck or anything as a kid, where if you pull silly putty apart very slowly, it behaves ductily, right? And it stretches out, and you can get it to stretch really far. So here's another example of ductile deformation due to shear stress. Remember, shear is that sort of transforms motion of 2 things sliding past each other. Here is of a fossil. So here's a trilobite. And here a fossil of a trilobite has been deformed ductily because of that stress. All right, so we have ductile deformation with our silly putty, and if we're going to ductily deform our silly putty, we're going to like stretch it out really slowly. And the other type of deformation is brittle deformation, and this is breaking, shattering of rock because of that stress being applied. And so this is where the silly putty example comes in, because if you have a big ball of silly putty and you pull it apart really fast, it actually breaks apart, right? Or if you have cornstarch and water and you pull it apart really fast, it just breaks apart. But if you pull it apart slowly, it kind of flows and behaves more ductily. So brittle deformation is when we break our rocks because of that stress being applied. So we get something cool in rocks sometimes, rocks that have been below ground for a long time and under high pressure. When those rocks when the rocks on top of them get eroded away, or those rocks that have been at depth get uplifted, like in a mountain building event. If those rocks that have been at depth for a long time very quickly come to the surface through some sort of mountain building event, they do something called exfoliation, where they sort of crack off as a result of that stress of the mountain building event. And you get long cracks or joints in your rocks called exfoliation joints, where they sort of crack off in layers, almost like this sometimes happens in rocks, but I don't know. I think I just noticed this because I am sort of a rock nerd, you know what I mean? But it almost makes me think of like a jawbreaker, like if you've ever like accidentally like broken the different layers of a jawbreaker off or something. That would be an example of sort of brittle feature in something that's not a rock. All right, so you might be asking yourself, okay, so stress is applied to rocks and they can either bend or break. Why do they do one or the other? And so how a rock behaves when stress is applied depends on a couple of things. So one is temperature. So just, and I think this kind of makes sense in our heads as we understand. Warmer things tend to be more ductile, colder things tend to be more brittle. Plastic behaves this way as well, where sometimes warmer plastic tends to be more ductile. But if things get cold in temperature, then they can behave more brittly, right? So rocks that are warmer are typically going to be more ductile. Rocks that are colder are going to be more brittle. This is because at higher temperatures, molecules and the bonds that hold them together can stretch and move around without breaking. Another thing that's important to determining whether we're going to have brittle or ductile deformation is pressure. So rocks that have greater pressure behave more ductilely than those under lower pressure. Right? So this pressure difference is why the crust is brittle and hard, but the lithosphere sort of flows plastically, right? Because it's under a little higher pressure. The rate of deformation or strain is important for determining whether we're going to have brittle or ductile deformation. So, for example, with the silly putty example, right, if you do gradual changes to your silly putty, then you're going to generally produce ductile deformation. But if you have a more sudden change, that's going to tend to cause more brittle deformation. And then composition of your rock, of course, is important. So we hopefully remember from identifying minerals and rocks in lab that some of our rocks or minerals are just softer than other ones, right? So think of those minerals in lab that you could scratch off under your fingernail, right? Think of gypsum or sulfur. That's just like a really soft mineral. A rock that has a lot of that in it, it's going to behave going to deform more easily, going to behave more ductilely than a harder, say, quartz based rock that's harder and it's not as easy to deform. All right, so take a second to think about these two questions, which are, what type of deformation would we expect to occur deep in the crust? So deeper in the earth, what type of deformation might we expect there? Think about temperature, pressure, rock composition, and then compare that to what type of deformation we would expect near the surface, right? Think about temperatures, pressures, and potentially rock composition and compare those two. Okay, so now we're going to talk about two different ways that we classify rock deformation. And these two different ways that we classify rock deformation are based on those two sort of classes or types of deformation or responses to stress. So the first of those is ductile deformation. Ductile deformation results in folds, right? Because we're folding, bending our rocks. We create something in our rocks that we as geologists classify as folds. The other classification in structural geology would be those features that are created from brittle deformation, and those are our faults. So we're going to talk about folds, which are the result of ductile deformation, and then we're going to talk about faults, which are the result of brittle deformation. All right, so folds are just bends or wrinkles in our rocks, in our different rock layers. Remember, excuse me, remember strata is just a fancy word for layers. So in our rock layers, we have different bends or wrinkles or folds that are created from stress. And remember, folds are the result of ductile deformation of our different layers. As we classify folds, we have a number of different components. So in our fold, we have a hinge or a hinge line. So just like a hinge of a door, the hinge is the portion of the fold where the curvature is greatest, right? So we have a fold here, and where that curve is greatest through the middle is what we call the hinge line. And then on either side of our hinge line, we have a limb, right? So here's like one of our limbs. Here's our door, right? Here's the other limb. Here's the wall that the door's connected to. I thought there was more on that slide, but I deleted it because it wasn't important. All right, so here's a fold. This is hard to do with just two hands, but here's our fold. Here would be our hinge line because this is the greatest curvature. And then we would have a limb and a limb. All right, so folds are bends in rocks created from ductile deformation. And we can't get away that easily. There are a number of different types of folds, and we'll talk about each one of them with their own slides. So we have anticlines and synclines, which are kind of opposites of each other. We have monoclines, which means just one single sort of change in hinge. And then we have domes and basins, which are also opposites of each other. All right. Our hinge line can be parallel to the ground, or it can be plunging or angled. And we'll talk about that a bit more as well. All right, so a monocline is just like a little step-like fold in our rock layers that has basically two flat parts offset by a steep zone or a steep fold, right? So we have otherwise horizontal or gently sloping topography, gently sloping landscape. In the middle, we have our hinge, and it's called a monocline because it's just one step. And so here in this diagram, we have our hinge line here. And then we have one limb and then the other limb. So a monocline just kind of looks like a step with a hinge line relatively flat otherwise. Here's an example of a rock outcrop in Wyoming with a monocline where you can see relatively flat layers. You're going to get this slope, and this isn't the best picture ever, but we have sort of this, our hinge here, and then as we get down here, it's going to level back off, like down into the step-like pattern. All right, so now we have monoclines, type of fold. Now let's talk about our anticlines and synclines. So anticlines and synclines are both arch-shaped folds. Our anticlines are like the St. Louis Arch, right? So anticlines are arches where the convex side of the arch is up. And if we're thinking about our principles of stratigraphy, where our oldest layers are at the bottom and our youngest layers are at the top of our rock strata. And then we fold this like this. And then that means that in our fold, the oldest layers are on the inside of our arch and the youngest layers are on the outside of our arch. So with an anticline, St. Louis Arch, because oldest rocks are on the bottom, youngest rocks are at the top. When we fold them in half in an anticline convex up shape, we get the oldest rocks on the inside and the youngest rocks on the outside of our arch. When this erodes away at the top, which this picture shows better than my thin little layers, what we see is that along our hinge, right? So our arch used to come up and it's been eroded away over time. What we see is along our hinge, we have the oldest rocks. And as we move away from our hinge, our rocks get younger and younger. So the oldest rock beds at the surface, we find those along the hinge line when we have an anticline. Here's an example of an anticline in Iran, where you can see here's our arch. If this was originally flat, we would see the oldest rocks are in the middle and the youngest rocks are on the outside. Anticlines. Synclines are concave up fold. So they're like a U shape instead of an arch. And so with synclines, again, still this basic fold. But what we see is because oldest layers on the bottom, youngest layers on the top, we fold it up. What we now see is that the youngest layers are in the middle. The oldest layers are on the outside, which means that along our hinge line, the youngest layers are going to be along our hinge line. The oldest layers are going to be farther away from our hinge, right? So with the syncline, youngest layers towards the hinge, oldest layers on the outside. So to tell the difference between an anticline and a syncline, anticlines are arch-shaped, oldest in the middle. Synclines are U-shaped with the youngest in the middle. All right, here's a syncline, which I have seen in my life, and I had to get out of the car and stop and take a picture of it. This is not my picture. You can tell by how old this car is. But all my pictures had like a bad sun glare on it. But I did go out to Baltimore for a conference, and we had to stop on our way there to take a picture of this road cut where we can see this nice syncline, right? We have this upward U fold where the youngest stuff is in the middle and the oldest stuff is on the outside. So the cool thing is anticlines and synclines often occur together in folded rocks, right? So I can do this and make an anticline arch shape and a syncline U shape together. We can see that on the diagram here where we have an anticline arch shape, oldest rocks in the middle, syncline U shape with the youngest rocks in the middle. Also important to note that when we're talking about folds in rocks, that scale is not important. And what that means is we see giant anticlines and synclines in the mountains. You can see this one's smaller. You can kind of see some like little trees hanging out up here. We also see these in hand samples. We see these, you can find them just like in rocks laying around campus. We can see them really tiny microscopically in rock cross sections that we look at under the microscope. And so the important thing to know about folds, scale's not important. We see these sort of at all scales in rocks. All right, so the last thing about anticlines and synclines is that, again, remember, we can have plunging ones, right? So here I have an arch-shaped anticline, and so far we've just sort of shown them parallel to the ground. But if you make that hinge line angled, then what we get is, instead of getting kind of perpendicular layers on the ground, we get these triangular or V-shaped folds or patterns at the ground surface. And so we get V or arch shapes. Here's a syncline here where you can see as it plunges down, we're creating this V shape. Here's our anticline. As you can see, as it's plunging down, we're creating this V shape. We get these different layers because some layers of rock are softer and more easily eroded away than other layers, right? So the ones that are hardier, the ones that are harder to erode away, they take longer to erode away, and they create these ridges or more resistant layers that kind of stick out of the ground and hang around for longer. All right. So in this picture, again, our anticline is plunging down towards the point of the V. So sort of, plunging down this way. Syncline is plunging towards the opening of the V. So if we use that information, knowing that anticlines plunge towards the point of the V, synclines point towards the opening of the V, then we can figure out what way is this whole landscape plunging, right? What way is this the axes on these plunging? And we can figure out that it's plunging towards us, right? Towards the bottom of the screen. All right, so here's an example of an anticline. Again, we know it's an anticline because here in our cross section, we can see oldest stuff in the middle, youngest stuff on the outside, arch shape. And we can see we have these more resistant layers that have not eroded as much as some of the less resistant layers. That's what this is showing over here. We have a hard sandstone that's more resistant than our softer shale. All right, and then the last two classifications of folds are domes and basins, which are similar to our anticlines and synclines, except instead of being flat strata that have just been folded this way, they get molded or folded all the way around into a bowl shape. And so domes are similar to anticlines, where we get this bowl shape instead of a instead of an arch shape. Think about, we take a bowl, we put our bowl upside down on the table. Our oldest rocks are going to be in the center of that. Youngest rocks are going to be on the outside. Similarly, basins, bowl-shaped structure, right? Like you would usually hold your cereal bowl, where it's very similar to a syncline, where the youngest rocks are in the center, the oldest rocks are on the outside. So we have folds, and remember that our folds are associated with our ductile deformation. We have those 5 different types of folds that we just went through. We have monoclines, anticlines, synclines, domes, and basins. All right, so now let's talk about faults. So faults are associated with brittle deformation, and they are fractures in our rocks created from this applied stress, where one part of the rock or one piece of the rock, one body of it, is going to slide past another. And again, fractures created from breakings, created by brittle deformation of our rocks. And in our faults, of course, we have some words to describe different components of them. And our fault line, or our fault plane, is the boundary along which that movement is occurring. So in this picture over here, we can see we have this nice tan light layer in our rock layers, in our rock strata. And we have this crack running between the middle that has offset this originally horizontal layer. And so this crack here is our fault plane. We would say this is a block. This half here is a block or a body. And then we would say this other piece here is another block or body. So fault planes are just the boundary along which movement occurs. And so fault planes can happen underground. If we see fault planes at the surface, then we refer to them as scarps. So fault scarps are just exposed fault plains at the Earth's surface. All right, so talking a bit more about fault blocks and components of faults. So we have our fault line here. Where it's exposed at the surface up here, we would call that a scarp. Underground, we just call it a line. And we have our two blocks or our two bodies. And we describe these two blocks, the two pieces on either side of the fault line, as either the head wall or the foot wall. And so the way that I figure it out the best is if you were standing on the fault line, the one that you would be standing on, the block you'd be standing on, is the bottom block. We call that the foot wall because that's where your feet are. And the hanging wall or the head wall, I like to refer to it as the head wall because it makes more sense in my head to call it the foot wall and the head wall than the foot wall and the hanging wall. But you'll see both. You'll see hanging wall and head wall. But the head wall is where your head would be if you were standing on that fault line. And so hanging wall, where your head wall is your top block, where your head would touch if you were standing on the fault plane. And the foot wall is where your feet would touch if you were standing on the fault plane. So we talk about the two different bodies of rock, the two different pieces sliding past each other along the fault plane based on head wall and foot wall. This is important because the angle of the fault line and whether the faults blocks are moving in certain directions, whether they're moving towards each other or away from each other, means that the head wall is going to move either up or down relative to the foot wall or side to side. And so if we have a hanging wall and a foot wall, whether they're moving up or down relative to each other can help us figure out what type of fault it is. So that's why those components are important. All right, so each fault type that we have is associated with a specific stress type. I should go back to this slide here for a second. There's two main types of faults. We have dip-slip faults and we have strike-slip faults. Dip-slip faults are associated with either compression or tension. They have an angled fault plane, and the head wall is going to be either moving up or down in association to the foot wall. In our strike-slip faults, this is where we have that transform boundary motion, that shear force. The fault line tends to be vertical in these types of faults. And instead of moving up or down relative to each other, because we have this vertical fault line, you can't really stand on it. So instead of calling it a head wall or foot wall, we just talk about the two blocks relative to each other when you're standing on one and looking towards the other one. And so we're going to go through each one of these types of faults in more detail. All right, so again, each of those fault types is associated with one of those specific stress types. When we have those compressive forces, this is when we have an angled fault line. We have a head wall and a foot wall. We get, and when we have compressive forces, we call that a reverse fault. So in a reverse fault, our rocks are getting pushed together. Our two blocks are getting pushed together. In extensional stress, we get what's called a normal fault. So again, extension forces, this is when we have two blocks moving away from each other and we create a normal fault, right? Because those two blocks are moving away from each other, they're getting pulled apart. And when we have those shear forces, those forces sliding past each other, we get what's called a strike-slip fault. And this is where those rock layers are sliding past one another. All right, so let's talk about those dip slip faults. Again, dip slip faults are when we have an angled fault line and we have a head wall and a foot wall, because we can stand on an angled fault line to figure out which one is the head wall and the foot wall. And when we have normal faults, again, this is when we have extensional or tension forces pulling those two blocks apart. And we have a non-vertical, right? We have a dipped or a tilted fault plane. And all right, so if we're standing on our fault plane here, that means this block would be our foot wall. That's where our feet would be. This one would be our head wall. That's where our head would be if we were standing on the fault line here. And as the blocks move away from each other due to those extensional forces, then the head wall is going to move down relative to the foot wall. So in normal faults, the head wall is moving down relative to the foot wall. All right, so let's think about the type of plate boundary where we have extensional forces pulling things apart, where we might have a lot of normal faults happening. And the plate boundary would be divergent. All right, here's an example of a normal fault where, let's look closely at this real world example. We have, here's our fault line. If we were standing right here on our fault line, the block we would be standing on would be this one on the right, which means this is the foot wall. And then our head would hit this one, which means this is the head wall. And then these rocks were all originally horizontal layers, so let's find a good marker bed or a good nice layer. This black one between the two white layers is a good one. We see it over here, and we see it over here. And what we see is it was originally flat line, but our head wall has moved down relative to our foot wall. And if our head walls move down relative to our foot wall, that means that we have a normal fault. Right? So maybe you can start to see how differentiating between head wall and foot wall can help you figure out when you go out into the field, right? Or you have examples where you need to figure out what type of fault it is, that those words are useful instead of saying like right and left and those types of things. All right, dip slip faults continued again. Remember, dip slip faults are the ones that have angled fault lines. We have two different types of faults, dip slip faults associated with compressional forces pushing the two blocks together. When we have a steep slope of our fault plane, so of our dipping, non-vertical tilted fault plane, if we have a steep slope, we call it a reverse fault. And so in a reverse fault, because we have these compressional forces pushing the two blocks together, what we see is if we stand on our fault line, this would be the foot wall. The one on the right would be the head wall. And we can see that because of these compressional forces, the head wall has moved up relative to the foot wall, right? So here's our like originally horizontal layer. We can see that layer on our head wall has moved up relative to our foot wall. Thrust faults are the same thing as reverse faults. They are associated with compressional forces and a non-vertical fault plane, but the difference is that there's a more gentle slope associated with thrust faults. I generally, for the sake of this class, I just sort of roll those all together, right? For us, not generally going to be important to differentiate between reverse and thrust faults. They're the same thing, just the slope or the angle of the fault line is different. If we have Compressional forces, where would we see, along which type of plate boundary would we see some good examples of reverse or thrust faults? The answer is convergent. All right, here is an example of a thrust fault. We call it a thrust fault instead of a reverse fault because the angle is not very steep. And so here is our fault line. This one's kind of hard to find a good marker bed, but here's a good one. These sort of like two white layers on either side. And so we have a good marker bed. We have our fault line. As we're standing on our fault line, we can see this bottom one on the right is our foot wall. This one on the left is our head wall. What we see is our head wall has moved up relative to our foot wall. And if our head wall has moved up relative to our foot wall, then we know that it's a reverse fault. And if we want to get fancy, we'll call it a thrust fault because the angle is low. Though reverse fault, in my mind, is totally an acceptable answer. All right, so the cool thing is in some places where we have extensional forces, right? So in basins where we have spreading, lots of things moving away, this sort of general movement of stretching out extensional forces, we get these cool features called Horst and Grabens. And so Horst and Grabens are just blocks that are bounded on either side with normal faults that have opposite dipping angles. And so what we get is like we have this general extension pulling these apart, and what we get is we get these down thrown blocks called Grabens. All right, here's our oppositely dipping fault lines. We get Grabens because we have this opposite dipping, get down thrown blocks, and up thrown blocks called Horsts. So Horsts and Grabens. And these are really common in rift valleys. So for example, in the Rift Valley of Africa, where we have a lot of extensional forces happening today, we're creating Horst and Grabens, but also the Southwest. So a lot of the mountains in the Southwest are associated to old rift boundaries where we had sort of this divergent extensional forces happening. All right, so dip slip associated with an angle of the fault line and moving of a head wall in association to a foot wall, either up and down. And we have sort of those two big examples of extensional forces or compressional forces. And then our big third class of faults is associated, or we call those strike slip faults. And again, these are associated with our shear stress, where we have a vertical fault line and then shear stress. So our two blocks are sliding just past each other. And we have two types of strike slip faults. We have left lateral and right lateral strike slip faults. And so again, because we have this vertical fault line, we can't use the head wall and the foot wall thing to help us out here. So what we do instead is we envision that we're standing on one of the blocks, and we're going to look across the fault line at the other block. And if we're looking across the fault line at the other block and the stuff on that block looks like it's displaced to the left, then we call it a left lateral strike slip fault because you're moving this way. This other block is appearing to move to the left in association with where you're standing on this block. Again, this is because we have this shear force along a vertical fault plane. So we have to think of another way to describe things instead of a head wall and a foot wall. And then a right lateral strike slip is if you're standing on the block and you look across at the other block and the stuff over there looks like it's displaced or moved to the right. Then we call it a right lateral strike slip. Again, shear forces on a vertical fault plane. So, strike slip faults. What plate boundary do we find strike slip faults along? Answer would be transform. All right, so let's say here's an example of a strike slip fault. Here is our fault line. We've got these marker beds. Here's some good marker beds. See how they're displaced. All right, if we imagine that we're standing here on the red star and we're facing the fault line and we're looking over, what direction does our purple star seem to be displaced? It seems like it's displaced to the right. And so we call this a right lateral strike slip fault because the stuff on the other side of the fault line from where we're standing looks like it's been displaced to the right. All right, so that is rock deformation structural geology. Like I said, I think this stuff is really fun, sort of like a puzzle. And it's, like cool. I don't know. I like it. So we will obviously do more with